All right. So it's a pleasure to have Jakob from Tel Aviv University here. And he will talk about this holographic inspired stringy hadron model. And please welcome him.
So thank you, Massimo, for inviting me to do this talk. And I'll tell you today about what I call the HISH model. It's a holographic inspired stringy hadron model. And I'll describe the properties of the spectra, decay processes, exotic hadrons, and finally, and this is something we know from last month, scattering amplitudes. And most of the work was done in collaboration with my former student, Dorin Weissman. But I have many other collaborators which I'll mention. I just wanted to say that I will not make justice in all the references that I have given. This is a topic that was discussed through the years by many people. All the references are our papers. I just mentioned a very few ones. So I apologize for that. Okay, so the idea is to construct a phenomenological string model, a unitary model that is supposed to be in accordance with as much as possible experimental data of hadron physics. And of course, the goal is to be able to predict some novel phenomena. Now, the model is in flat 4 dimensions, but it is inspired. It came from ideas from a holographic string model, namely in higher dimensions, discrete space-time with Ramon Prince and so on. Now, eventually, the challenge is to relate it to QCD. So the construction of the model is based on the following steps. The first step is to determine a prototype confining holographic backgrounds. Everybody here is familiar with the HS5+5. This is not a confining background, so the question is, how do you deform it to get a confining background? So I'll discuss it very briefly, and once we have such a prototype model, we can try and analyze, and that's step 2, analyzing classical stringy solutions to the questions of motion. And these strings will correspond, some of them to mesons, some to baryons, glueballs, and so on. Once we have them as classical solutions, we want to map them into solutions in flat 4 dimensions. This is all classical at that point, at this point. And in particular, if I want to get hadrons with angular momentum, I'll use rotating strings. And so this map is not something which I can derive. It's not a controlled approximation. It's just, if you want a guess or inspiration that we get from holography. But then we want to quantize it. So the point is that it's very complicated or probably impossible to quantize strings in a Ramon background and in general 10-dimensional superstring theory. But once we use this map to go to 4 dimensions, then the task of quantizing is much simpler. It's still not very trivial because it's a quantization with strings with endpoint particles which carry masses, spins, charges, baryonic vertices, and so on. So it's complicated in general to quantize such a system, but for certain limits, like for small masses or large masses, we can do it. Now, the quantization involves also the renormalization of the worldsheet Hamiltonian that we do automatically by doing the zeta function renormalization, we should say. But this cannot work now, and we will have to develop a new tools, new methods to renormalize the string. And apparently, the idea will be to use something which is very similar to what one does when one quantizes or one discusses the Casimir effects. Okay. Now, one important thing is that I mentioned that I'm moving to 4 dimensions. Now, the one loop beta function in 4 dimensions is clearly not vanishing. It's not conformal on the voltage unless you add the Liouville mode, or we will call it Puczynski-Strominger mode. So you have to compensate the ordinary transverse direction also with these Liouville modes to have a system which we can discuss in non-critical dimension. Now, once we have performed this quantization, then we go to the data and we extract using best fits the values of the parameters, which will be the string tension, that's or the slope. We'll have endpoint masses, if you want the masses of the quarks, and we will have a bunch of intercepts, and I'll discuss it soon. So that using that, I'll show you that we can have a very nice fits with most or all the trajectories of hadrons, both baryons, both mesons and baryons. Then the next challenge is to see not only the spectra, but also the decay processes. So all the resonances that we detect, apart from very few, are unstable, strongly unstable, and you want to be able to compute the total decay widths, the branching ratio, and so on. And it's essentially based on the process of a breaking of a string into 2 strings. So that will be the decays. Then we will analyze this more exotic stuff, which will be both glueballs and hadron, exotic hadrons like tetra quarks and etc. The new stuff is that we have done recently in collaboration with Massimo Bianchi and also Firota is finding a way to get scatter amplitudes which are partonic in the nature, starting from stringy amplitudes which are soft. So the problem that was the reason, in fact, that string theory was abandoned from a description of hadrons. The fact that in the deep inelastic scattering there was this mismatch between experiment and theory, but using holography, it was shown already some time ago by Puczynski and Strassler, and we developed it further that one can get partonic behavior from string scattering. Okay, and then finally we want to have predictions. So let me start with the first is what do we mean by holographic confining background? How do we define them, and how do we construct such backgrounds? So there are various properties of confinement that one can try to mimic in this holographic duality. The one that we're using is a Wilson line. So this Wilson line, or if you want Wilson-Margasena line, is a quantity that we compute in the stringy background. And so basically on the boundary, we put 2 endpoints, and then we compute the Nambu-Goto, the solution to the Nambu-Goto action, which determines the profile of the string. It's divergent, the action. You have to renormalize it, but once you do it, the question is, do you get a result which is linear with the separation distance or not? If you do it in ordinary ideas 5 + 5, if you want to be linear with L, it will go like 1/L, nearly conformal and non-confining, but there are backgrounds where it is linear in L. That is what we are after. So what is the condition to get a background that admits this confining Wilson loop or Wilson line? And So if you start with a general background, but these are the space-time direction, this is the holographic direction, these are transverse directions, then we found out that there are two sufficient conditions. So either you have that this quantity G00 times GXX has a minimum and the value of this quantity at the minimum is positive, or this quantity G00 times G diverges, and at this point, again, this quantity is positive. This F is in fact a string tension, or the string tension is proportional to that. So once we have it to be non-vanishing, there is a string tension and the system confines. For instance, if we take the radius 5 plus 5, then the minimum is at 0, and the quantity, this quantity will be u squared or u to the 4 at u goes to 0 and it vanishes. Whereas in certain models, like the Cleveland cluster and other known as, this condition has been obeyed, and in the so-called Witten's model, this condition has been obeyed, and they will admit this linear Wilson line. Are there any questions? Yes.
So here, are you assuming that there's no B field that's turned on?
Well, on top there are additional dilaton, Ramon. I'm considering just the metric of the background. That once I have the metric, this is a sufficient condition to have this property.
But is it assuming
It won't be spoiled by having additional fields on the background.
the B field would affect, for example, that will go to action. So that
Right.
could modify
So
the
this is
behavior.
assuming that there is no B field.
It is assuming.
Mhm.
So if there's a B field, there are more possible
Right.
solutions.
Even
Yeah.
though I think that it will remain this. So once you obey this condition, but this is without this additional
Okay.
fields. And also, of course, it's a particular case where the dependence on the background is only on the holographic coordinates. Holographic coordinates. So let me demonstrate it by the so-called Witten's model, which is a model of a compactified D4 brane. So that's a 10-dimensional metric, and it has an ordinary 4 flat dimension, but with a warp factor. And there is one coordinate of the D4 brane, which is compact, and together with the holographic direction, it forms a cigar. And this cigar sets the minimal value of the holographic coordinate u lambda. So this is where a scale is put in this otherwise conformal background. And if you follow this red line, that is the Wilson line that will be confining. It will be linear with a separation distance. And on top there is this additional S4, which will make use of, and unlike the radius 5 cos 5, its radius is not constant. But this is a 10-dimensional solution of Einstein's equations in this case type 2A. And this will be a dual to a theory, a gauge theory with the confining Wilson line. Okay, but that background is a dual to a pure gauge. Now the question is, how do you mimic quarks or flavor? And that is done by adding flavor branes. So it turns out that a very successful model is the so-called Sakai-Sugimoto model. So what you place asymptotically a set of NF-D8 branes and anti-D8 branes, but because of the topology of this cigar, they have to merge. So a priori, we have U and left symmetry here, and U and F right symmetry here, which is broken down to the diagonal, and that is a geometrical realization of chiral symmetry breaking. And Sakai Sugimoto had this antipodal construction. For us, it will be very important that it's not antipodal, and there is this height here. But you can show that this is a solution, and moreover, this is not always very convincing that it's stable. So you may think that small perturbation will bring it to antipodal. That answer is no. We did so this all this is done in the limit of NF over NC, being very small. We did the back reaction analysis, and we found that is stable.
So just a question here: the branes extend inside the space, or
well, so these have 9 coordinates,
Mhm.
and one of them is unspecified in these 2 dimensions. So that will be the perpendicular here, or the perpendicular here. So altogether we will have 9 coordinates to this DA brane. Okay. So now in this Witten's model or the Cleveland Trust or any of this model, we will analyze now stringy configuration. That will be model independent, as long as it's a confining backbone. Okay, so I want to emphasize the point. In this sense, this approach is somewhat different than other holographic approaches, in the sense that we are not using the duality between bulk fields and operators on the boundaries, but rather use strings. So this bulk to operator is based on this alpha prime goes to 0. For instance, we go from closed strings to gravity. But we know that, as I showed you, this for the Wilson line and for also Truft line and Polyakov line, you cannot use fields. You need the string. And the main point of our work is that also for the spectra and other properties of hadrons, we need strings in holography, not fields. Okay, so we now go and look for classical solution of the Nabu-Goto equations of motion in this kind of backgrounds. So, for instance, we will. Well, it's type 2, so you cannot have strings ending on any point in space-time, but rather only on this flavor brane. So you have 2 endpoints of string, you compute the profile, and you look for rotating solutions. If you want angular momentum. So in this generalized Sakai Sugimoto model, it will look the following. So we have a string that connects the tip of this the 8 branes in one point in space and another point in space, and this configuration all rotates. Now this is not very complicated to solve this profile, and it's clearly much simpler than doing anything in the background with Ramon robot and higher dimensions as curvature and so on. This is, for instance, a B meson. So a B meson will be a string that connects a point on the flavor brane of the B and the light UOD flavor brane. So that will be this configuration that we will consider the stringy description of a B meson.
Very cool. Just want to make sure. So, are you saying the 10-dimensional solution does not have a remote flux?
Well, I'm saying that now I move to the 4 dimensions, which is flat 4 dimensions with no remote and nothing but ordinary strings in this flat 4 dimensions. Yes.
But the original 10-dimensional solution does have.
What I'm saying is that if I'm looking on the equation of motion that determine this solution in this classical solution in this higher dimensional, I can map it. I'll do it in a second. This is before that, but I can. There is an equivalence between the equations of motion in the higher dimensional space and photon. I'm coming to it in a second, okay? Now with me,
Jacob?
yeah,
Hi, sorry, there is also a question from Glennis.
yes.
Hi. Do the are the endpoints where the quarks are those fermions, or is the theory, how does the theory?
Well, now it's bosonic string. Now on the endpoints, I'll then address it later with other structure. The first will be just masses, then charges, and then eventually also spins. And in that respect, the endpoints will be fermionic. But so far, everything is bosonic.
In principle, would there be a fermionic string theory that you could do this with, right from the start, or?
Well, I mean, what it is now described. Let me come to the map, and then I'll
Okay.
but
Okay,
so
good.
far, everything is bosonic strings. Okay, so we want to go to. Okay, before I go to the map, I just want to mention another class of configuration, and that is what are baryons. So I claim that a quark is an end of a string. So to have a baryon, I need something that will be connected to NC string. And that was a proposal by Wittgengoss and Noburi to take a wrapped DP brane that wraps a p cycle, for instance, originally the D5 brane over S5. And due to the amount flux, it's easy to show using the Chern-Simon theorem of the action that there must be NC string connected to this object. So how does it look like in a cartoon? Simply that we have this wrapped brane, and there are NC strings that can either connect to the background, to the boundary, or to a flavor brane. But if it's a dynamical baryon, it's clearly it has to connect to one of the flavor branes, one or more than one. Now we can have different layouts, a symmetric one, an asymmetric one, and what will be chosen is, of course, a configuration that has the lowest energy. Okay, so this well, meson baryons and glueballs are now quarks associated, so it will be simply a folded closed string. Okay, and now we come to the heart of the story, to the main part, and this is the map to HISH, the map to flat four dimensions. So if one look on the equations of motion in this higher dimensional part, there will be an equation of the segments, which are the vertical ones, and the horizontal ones. Of course, it's just an approximation that one can split it in this way, but you can we show that the equations of motion of the two systems, of this holographic system and of the system of a string, bosonic string with massive endpoint, the equations of motion are the same, provided that we define these masses to be the action associated with the vertical segments. Okay, so this is a new type or a different type of quark mass. It's not a QCD quark mass. It's not a constituent quark mass, but it's rather string endpoint quark mass. And it is defined by the action along these vertical segments. The longer the string is, then this approximation is, of course, better. And it turns out that if you plug the boundary conditions of these strings, they take the form of the balancing between the tension and the centrifugal force. Is it clear, or the questions? Now, once I have this classical solution, I can calculate the net current associated with the shift in space, in this shift in time, and shift in some angle in some two-dimensional plane. So I'll compute the net energy and the angular momentum, and it gets contribution from the endpoints particles and from the string. And we have now an expression which is a modification of the original Rager behavior. So what was the Rager? The Rager form was that J was proportional to alpha prime, the slope times the mass squared, or the energy squared. And now this expression I cannot, this is based on eliminating the lengths for one equation and plug it in the other, but this cannot be done in general. So we have a parametric relation, but for the cases that beta goes to 1 or beta goes to 0, for small masses or large masses, we can derive an expression. So the classical Rager is modified by alpha prime m squared multiplying 1 minus this expression, where we have a dependence on the ratio between the masses of the endpoints and the total mass. But I want to emphasize that later when I do the feeds, in the feeds we use the general expression, we don't use the limits. Okay, so so this will be, for instance, again, the map of the holographic configuration to a flat string. And for the baryon, it will be either a symmetric object, which will, for n equal to 3, will be that Y shape, or asymmetric, which will be a quark diquark. And I want to argue first theoretically that the Y shape is unstable, and that was analyzed originally by Schaub and later by Truft. They showed that if you take the Y shape and you shorten one of the arms slightly, then it will collapse and eventually you'll get a single string. With a student, we checked it by doing numerical simulation, and indeed in a more general setup with massive endpoint, and didn't find that it's unstable, but it's not perturbatively, it's unstable. Okay, so, and this is a cartoon that summarizes with light quarks how you get mesons with charge -0 or plus, baryon for minus to plus B plus plus. So here, for instance, you have a diquark of 2 UUs. On the other side, you have another U quark.
Sorry, but this is in this picture, which I think is still at least morally the holographic one. The brains do not extend into the radial direction. Right? Brains seem to be fixed.
Well, okay, so this, what determines the brains is the solution of the dBi action in that background. Mm-hmm. Similarly to the solution of the profile of the string, there is a solution of the. Now you've seen that in the cigar, the brain has a U shape. Mm-hmm. That's a solution of the dBi, but in ordinary flat space-time, they are really flat. But the point is that I won't use this. I will use this picture where it's really in 4 dimensions. Okay, so next is a story of the quantization. It's a long story, and I want. How much time do I have?
You have still 30 minutes. Or...
30 minutes.
Yeah.
Okay. So the quantization of this string, this is massive endpoints, was dealt long time ago by Chodos and Thorne and others, but in fact it was not worked out all the way. And for the case for small masses, we did it now. So okay, so let's start with the ordinary string with no massive endpoints. Then the classical rotating string goes into this famous Rager trajectory. If it's not in the ground state, it's in an excited state. That's the expression, the quantum expression. And this A, the intercept, is in fact the Casimir energy. So the sum over the eigenfrequencies of the string gives the Casimir energy in the form of A over L, where L is the length of the string. So the challenge is to compute this quantity A. It's simply the zeta function when omega n is n. But for the massive endpoint, omega n is not n, but it's a solution of this transcendental equation, and which we cannot solve analytically, but the solution has the following form. So this is for very large masses. It goes, for instance, for the level 4, it will go down and we will match the one to level 3 and so on. So these are the profile of omega n's. And we have to, for any given point here, which is means the masses of the endpoints, we have to solve for the sum of all the eigenfrequencies. Now, as I mentioned, we cannot use the zeta function. We'll get, in particular, zeta of 1. And so we needed another method. And the method is that was suggested by these people the first time, is to translate this sum that we want, the sum of omega n's, into a contour integral using Cauchy integral formula. So we'll pick a function with simple zeros and no poles, and we want to perform this integral, this contour integral, to get the answer for the sum. Now we have to regularize this integral, so we take a radius of radius lambda, and so we'll have to do this sum. We have to do the integral along the imaginary part and the semicircle. Now, once we have the regularized expression, you get the renormalized one is by subtracting, just as we do with the ordinary Casimir effect when we take the two plates to infinity. So we'll have a string of lengths infinity. The subtraction is in fact not, as written here, of the energy, but of the force. So you have to first differentiate. But if we do it, for instance, for the massless case, then the function will be simply sine of pi omega L. And we'll have a part of the integral which comes from the imaginary axis, and then this semicircle. And the result is the following. So it's this lambda square times L and 1 over L. So the force is this expression. And if we subtract from that the force for L goes to infinity, we are left with this, which we integrate back to get the energy. That's the same result as the zeta function, but I'm not showing you now the computation with masses, but it's much more complicated. The function is not as simple as I showed, but we did a calculation, and you get a contribution from d-3 transverse to the plane of rotation, one planar, a mode, and then this Polchinski-Strominger, which is the Liouville mode. So altogether, the intercept looks as follows. There are these transverse modes. So what we have here is the intercept, for instance, from minus 0.5 to 1 as a function of beta. That's a velocity of one of the arms and the ratio of the masses of the arms. And you see when we are these black lines, we go from positive to negative, which you will see in a moment is very important for us. We don't have negative in the planar, we don't have negative in the Liouville or Polchinski-Strominger. That's the total result. Now, okay, so I'll move on and go and talk about the best fits to the data, and I'll come back to this issue with the intercept in a second. So we took the trajectories of rho, omega, k star, phi, d, and psi, and also baryons, and we came out with these values of the quarks in MEV. The slope is alpha prime is 0.9, and we get a bunch of intercepts. But notice that the intercept minus the spin, so it's the intercept with respect to the rotation, the orbital angular momentum, it's always negative. So this is for mesons, vector mesons, and scalar mesons, but it's also the case for baryons. So why is it so? Why do we need negative intercept? The reason is very simple, because negative intercept means a repulsive Casimir force. When you don't have rotation, the only thing that can balance the tension is this repulsive Casimir force. And in fact, we see from the data I'll show you now that indeed, as you can see from the table, that these quantities indeed come out to be negative. That's the reason that we don't have the Koenig states, and the string does not collapse to zero size.
So these intercepts are not independent parameters, are fixed in terms of the masses.
Well, they do depend on the masses.
But these numbers, I mean, are fixed. Once you have
These numbers are of the whole trajectory, but in fact, if you compute them, they will depend on the masses, as I showed you in this picture. So you see that they do depend on the masses. But what we extract from the data is one intercept for a trajectory. And
what I don't understand is that now you have two parameters. You have the masses at the end of the of the string, and then the intercept. But
That's
the
right.
intercept is a function of the masses. So
Right.
once you fix the masses, you have the intercept.
Right, but I mean, what we do is somewhat different. For instance, this is a trajectory of the isospin scalar omega and eta. You see, it looks very much like a line, and so we can just determine in this m squared as a function of j the intercept. If it's later when it bends, you can still determine this parameter, which is the intercept. And notice that there is a nice agreement between the lines and the blue points, which are the experimental value. So this is for strange mesons, K and K star. You start to see the bending. That will be SS bar with the phi. And this will be charmed one. And the charmed strange, and so on, CC bar, and the B's and B's. And clearly here you see that it's not anymore the linear rigid trajectory, it's banded because of this heavy masses on the endpoints. But still there is a nice agreement with the data. What happens with the baryons? So with nucleons, like quarks, it's very linear, but there is a different phenomenon, which is that the even and odd angular momentum, they have very different intercepts. And there are several explanations for that. I will not enter it now, but this is a feature of not all the baryons, but the nucleons and the delta, which I don't have here. These are the fits for the lambda, for strange, and then for sigmas and so on. Okay, so I think that from the set of parameters that we feed the masses, the slope, and the intercept, we can get many more points that are in accordance. And that's what I said, that there is a nice agreement in the spectra of this model and the data. I want to emphasize that's important, that these hadronic strings are very different than ordinary strings. The spin 0 is not a tachyon, it's a massive vector, it's a massive scalar meson, and the spin 1 is not a gauge field, it's not masses, but it's a massive vector meson. Okay. So now we'll go to something which is, I think, less known, and that is how do we describe decay processes of hadrons? And for that, we go back to the stringy picture. For instance, in type 1 open string, the strings can definitely open, they can split, and we have such a Rothschild diagram. For us, it will be that the endpoints are addressed with massive particles. And the question is, what is the amplitude for such a process? Now, if you think about it intuitively, you would imagine, you would believe that it will be linear with the length of this string, because it can break at any point. But the question is, what does the calculation mean? So the idea is, of course, to use the optical theorem. We get that this width is given in terms of the imaginary part of the self-energy. This is a complicated anomalous diagram in string theory, but Polchinski had a clever trick to use one coordinate, to compactify one coordinate and take the string to wrap it. So in that case, what he computed is a closed string that opens and then closed again. So we have a diagram of a closed string, and this is a strip, an open string, and that's a closed string again. So for that point of view, here we have a full closed string. Here it's open, and again the closed string. So if we look at this part of the open, it's a disk. There are two closed string vertex operators. So that's not a complicated exercise. It's a 3-level string exercise. And if you calculate it, and we are interested in the dependence on the lengths, we get certain dependence from zero modes, from normalization factor, and eventually, at least for long strings, we get that indeed it's linear. So the width is linear with the length of the string. Now the length of the string, remember, is a function of the total mass of the string and the massive endpoints and the tension. But it's a simple expression to write the lengths given this value. So we know that the prediction here is that the total width is the tension times the length with some universal dimensionless coefficient. And this is for long strings. For shorter one, we also have to address it with some phase space factor. And so that is the total width. And the question now is, what about branching ratios? What is the probability of some given breakup or some given process? And for that, we have to go back to holography. So the idea in this HISH, we do some of the calculation in holography, and then we translate them, we transpose them to the bosonic string. So what does it mean to break a string in holography? It cannot break at any point, but only when it hits a flavor grain, right? So the question is, what is the probability that a string that stretches along the wall will hit some flavor grain? That's an exercise that one can do. We did it by describing the string as a string of beads, and also we can do it in a continuous way. Okay, so the breaking, it can be of different forms. You can break with creating a pair of light quarks or a pair of heavy quarks. And the result of the answer is that perhaps as e to the height squared over alpha prime, which translates to e to the minus n squared over t. This is, if you want, the stringy version of Schwinger mechanism. Massimo was doing in the past, and this was also analyzed derived in from QCD, like arguments by Kasher, Neuberger, and Nusinov, and they had that it's e to the minus m squared was a for constituent mass, and for us it's a much smaller masses for light quarks, you've seen. But there is also a difference between their tension and the one that we get from the fits. So altogether, this expression, once you correct it with a massive endpoint, curvature, and so on, is of this exponential factor. Now, I want to go to the data now. So we analyze several states of higher states of the rho, omega, and so on, and we looked on the decay widths, and it turns out that indeed you get that there is a universal factor here, which means that it's linear with TL. So for light quarks, measurements of light quarks, it's around 0.1 up to a few percent. Once you go to heavier, it deviates. But at least for light ones, we have a universal formula which works pretty well. Now, that is the way that it looks for decay of omega pi eta k star phi d star. Sometimes there are deviations, but otherwise it's the fit is okay. Now, also this ratio, this between different breakups. So for instance, if you compare the breaking into a pair of SS bar versus two light quarks, then you get that this factor is 0.3 when you plug the masses. And that is also realized in certain, there are not too many cases that we get this breakup to SS bar, but the ones that we found are in agreement with this number, and also for radiative decay. Okay, so how much more time have we got?
10 to 15 minutes.
Can I interject a real quick question about those
Yes.
things? I remember on an earlier slide, you showed that you said that it looked like a sort of substantial discrepancy with the phi mass. And somehow within this model, I guess everything needs to be gotten right. And then also you didn't discuss the eta prime. And I wanted to know whether the holography was smart enough to know about the axial anomaly and get the eta prime right.
Oh, okay, I'll be happy to discuss with you privately about it. I mean, there is some issue, some problem with the so-called Goldstone boson. So the pi comes out lower than the trajectory, and so also in some sense the case, and so this there is a less nice fit than in the rest of the hadronic states. Okay. Yeah, so there is a point about this pi, the k, and the prime, and I'll talk to you about it privately. I want to.
Okay, thanks. I didn't want to.
Okay, so let me now so we want to go ahead now to discuss exotics. So the first type of, it's not really exotic, but it's a glueball. So what is a glueball? It's a folded closed string. Since it's folded, you see it's like two string, and therefore the tension is twice the ordinary tension, and the slope is half, and the intercept is twice, like having two strings. And so now the question is, if you take all the data of the, and we really went to the PDG, it's not a job that we took really, I don't know, 15 or so, 0++, 2++, and we try to put them all in trajectories of mesons, and it does not work. So it's clear that at least some of the states do not sit nicely on the mesonic lines, and one attempt that we have is that we took two of them and we put them in this global trajectory that has twice the slope, and the others are two states on the light and of SS bar. And so it looks like the following. We have these two states, the green line, which are a global trajectory, and the others are a meson trajectory. Unfortunately, it's only 2 points that we can identify here, and we need some more to really trust it. And unfortunately, in the range of between 2.4 GeV and the CC bar threshold, there are not much resonances measured, so we don't know. But now there is a new experiment, the Panda experiment, and I think that they will be able to explore this region, and then we will see whether indeed we can disentangle this global trajectory from the meson trajectory. Now, let me now talk about, and I want to also mention, this is, Sergey is not here, but so there is a claim that when you do this lattice simulation of glueballs, then the results are NC independent. They do it for 3, 4, and so on, and they can claim that it's also larger. But there are structures that are clearly very sensitive to the to NC. So if you take a global not as a closed string, but as a set of NC string connecting a baryonic and antibaryonic vertex, then the mass is linear with NC, and the slope is 1 over NC. So clearly in these cases, you will distinguish between finite n and large n. And you can have all kinds of other bizarre configurations, which are all glueballs. Okay, I want now to go to tetra quarks. This is popular these days. So let me focus for a second on the charm hadrons. So that will be a meson which connects C and C bar. And in this HISH picture, this way, this will be one possibility for a cascade CC. So there is a diquark of CC and a U. It could have been also a diquark of CU and the C on the other side. Then it's not difficult to draw also a picture where there is a baryonic vertex and another antibaryonic vertex that they are connected, and we have here a system of 2 quarks, 2 antiquarks, and that's exactly the quark. Now the question is, well, this is another example, not with, so here the diquark is a CU and C bar U bar. The question they say is, when is it that it's the molecules and when it's genuine exotics? And in this picture, there are 2 ways to identify the real genuine tetra quarks. So if it's really a string, then there will be a Regge-like trajectory for the string. We can calculate all the state on this trajectory. And if this state, the excitations will be identified, then it's clearly a string, and it is a genuine tetra quark. And there is another important difference, and that is that I first noticed when Bell found that there is this resonance that decays into lambda C lambda C bar. So it decays into baryon antibaryon. Whatever decays into baryon antibaryon is a genuine tetra quark. But sometimes the masses are below the threshold that they won't decay that way. So we have to distinguish between the different. That's similarly for lambda B, lambda B bar. So I want to explain this decays. This is decay when the mass is above the threshold. The string will break and we get baryon and antibaryon. If it's below the threshold, then there is a probability of annihilation between the BV and the anti-BV, and we'll end up by 2 mesons. So we have 2 classes of decays, if we are in this mode, then it's clearly genuine exotic. If it is in this decay, we don't know. So we have to see for the excitations and to hopefully get this decay into baryon antibaryon. Okay, we analyze the particular case, and we'll skip it now. I want now, this is for you, Glenis. I want to go to this scattering amplitude. So everybody remembers that string theory was abandoned as a description of hadron physics because scattering amplitude does not work well. So this is the basic setup of 2-to-2 scattering. And if we use Veneziano amplitude and we go to the large S fixed angle, then we get a soft amplitude. So the amplitude behaves as alpha S is simply alpha prime S plus a constant. So it's exponential. But in the SLAC, in the deep inelastic scattering, it was found that the form of is power law, and it's not of this form. That was one of the reasons that people abandoned string theory as a description of hadrons. And Brodsky and Faraday, they made they had an argument why the amplitude should be of this form, where NP is the number of total number of partons. So, for instance, for pi nucleon scattering, we'll have NP equal to 10, and then A will be S to the -3, and the differential cross section will be this form. Now, how do we go from the soft behavior to the hard behavior? So Puchinsky and Strassler suggested a prescription in holography to do it. And we follow the idea. So the basic idea is that the string tension or the slope is not a constant, but rather it depends on the holographic scale. This property comes from the fact that you have to go from the momentum in 10 dimensions to momentum in 4 dimensions, and then that involves the holographic coordinate. Okay, so if you now make this map and you plug it into the expression of the amplitude, so we'll have that, for instance, in the so-called holographic hardware model, we have to integrate from R0 to infinity of integrating over the holographic coordinates of the amplitude, the stringy 10-dimensional stringy amplitude, dressed with some supergravity wave function. So that would be the weight that we give at any holographic coordinate to the amplitude. So you place for close string, you place this Virasoro-Shapiro amplitude, and it's easy to see that you indeed, and so we take simple-minded wave functions, we plug them inside. So the 10-dimensional was soft. Remember that since we get in this integral, this S over R squared, we integrate over R, and we get this Brodsky for our type of result, which translate into QCD language into this expression. And I just mentioned that we've done this type of calculations for the hardware model, the software model, Witten's model, and we got all the results, this kind of behavior. It was not always the same final result, but it's of a partonic nature. And we did this similarly also, the calculation for the Regge regime, not only the fixed angle, and also expanding around the poles. So we showed this passage from soft to hard. This is sometimes referred also as the bending. So if you look on this trajectory. So for positive t, you see the linear behavior, and when t goes to minus infinity, it bends and you get a constant value. Okay, so I probably ran out of time. I'll just show you that we can also do predictions. So we go to each trajectory and we go one state higher. For instance, for these values of j, or for higher values of n, the excitation numbers, and we get a value of the mass and the width, and hopefully they will be discovered. Okay, so I'll just mention several open questions. There are plenty of them, but an important one is this story of this repulsive Casimir force, this negative intercept. We don't know really how to get it in all cases. I mean, if we have asymmetric masses, for instance, no mass and massive, then it gives a negative value. But we need it also for the case that the masses at the endpoints are the same. Maybe we will need fermionic fluctuations, but that's not very bizarre in the holographic context, but it is bizarre if you want to relate it to QCD. So this is a big question. Then we want to discuss quantization of strings with charges, but that do not sum to zero. Massimo was working in the past with systems that have a Q and minus Q, and it leads to this non-commutative geometry and these values of an intercept that you place in the electric field, you get complex intercept. There are all kinds of interesting, but that was all for the neutral. For the charged one, like for the proton, there are still open questions there. Then, as you asked before, Glenis, there is this issue of what if you place spins, which we have to do it because we know that the row has spin 1 and so on. So how does this boundary conditions of spin affect the bosonic string? And then the question is, how do we go from this partonic cross-section to the total cross-section that is being measured by, for instance, the totem experiment in the LHC? So there are plenty of open questions, but I think that I'm not the person I'm not very objective about it, but I think that it's fair to say that it's very difficult to get results of hadron physics from QCD. And it's very easy, well, it's much easier to get it when you have some string model. And that's the purpose of this attempt. So thank you.
Yeah.
So still, I don't understand if the intercept in your model is fixed from data, so it's a phenomenological parameter, or if it's derived or from all.
Unfortunately, we get it from the data. We cannot. Well, I mean, we know what we have to do. You have to quantize the system, the string, with the boundary condition that you have, whether it's masses, charges, spins, and so on. Do the full process of computing the sum of the eigenfrequencies. That will give you the intercept. But we cannot. We don't claim that we have a theoretical model that will be in accordance with these values of intercept that we get from the data.
There was also something when you look showed the intercepts for various trajectories, for the pion, the eta, etc. There was something that I didn't understand. So you had.
Oh, but by the way, I just forgot. I have to. This is a very important slide that I forgot. So these are the people that I was collaborating through the years on that, including Recall and some other people that you know. So yeah, okay. Let me go now to your question. So you want to see?
So you had, say, the trajectories for the various mesons and then the averages.
Yes. Okay, so these are now the nucleons.
Yeah, then you had a table with the intercept and
Yes.
and pi and eta, I think, had two different values, but the average was the value for the eta, if I recall well.
Well, let me show you the table of the values. So these are the values of the intercept directly, and this is the when you subtract the S. So this is what we get for the rho and the omega.
It was another table. Yeah, it was another table a little bit later.
By the way, here you can see for any pairs of endpoints. Okay, now you want to see.
See if I can. There was a table that you showed later. Later was a table, just a list.
Values?
Yes. So let's see. Was it?
When we did this prediction, you mean?
Yes.
Okay.
Oh, okay. Yes, yes. So that a little bit back. 1, 2. Yeah, here. Pi is minus 3.4. Eta is minus 2.29. But what does it mean? Pi and
These
eta
are these A minus S values. So
minus-
for instance, for the rho, it's A is half, and when you subtract one, you get this roughly minus, and similarly for the pi, it's what you get.
But why the average of pi and eta is minus 0.29 and not a number in between 0.34 and 0.29? I mean, you have the same number of states, right? So I was just trying to understand what you mean by average.
Well, averaging where? In
You
this
have to
set?
say pi and eta average, right?
Then yeah, okay, I don't really. So instead of doing it separately, we took both of them, and well, you are worried that it was not shifted a little bit, or
Well, that
So
it was
here we
exactly
can-
the value for eta, and since that pi doesn't count.
let me show you what it really means. Just a second. Let's go for a second to the pi's. Okay, so you see, these states are the measured trajectory pi 2, pi 4, and so A1, pi 2, pi, and similarly you have also for a trajectory of the etas. So the distinction is between the isospin scalar and isospin vector, right? And so this is what we have. This is what you have for the etas. And then what we did, we took and we mixed together the etas and the pi's, and that's the value that we got there. I don't think that there is any significance to this.
No, because I thought that since the pi's are 3 states and the etas 1, let's say, because the value would have been closer to the pi value, not to the eta.
Well, I can check explicitly this. But you see, the main point here, Massimo, is that if you notice that they come out to be all very close to 0.1. And that's not guaranteed. Why is it that all of them have the same universal formula? That's exactly this linearity between gamma and the lengths, and it's up to a few percent here that it's 0.1. I don't think that there is I don't know how you calculate, for instance, decay widths of higher excited baryons in the skill model or in any other model. I don't know what they get in the lattice when they do such calculation. If they do, but this is a nice agreement between a very simple formula that gamma is linear with the length and the outcome of the.
Actually, I have a related question on this slide. Maybe I'll just inject it. It would help to have a comparison. You have the chi-square per degree of freedom for your model. if you did the same thing, just taking a linear trajectory, it would be very interesting to see how much this improves over linear trajectory.
To do
do you
what?
have-
I
Well,
didn't.
the old-fashioned idea was that the trajectories were linear. And an interesting question, so you have a curvature predicted for your trajectory. So a question would be, does the data support your curvature? And so
Yes, yes. So even for the light ones, we did the chi-squared values for the linear and for the nonlinear, and for the nonlinear, it's somewhat better.
I would love to see the same plot with another column.
It's difficult to see it from the plots, but we have the values of chi-squared.
No, I meant in this table. It would be great to see the corresponding chi-square with just a linear plot, just to get a sense of because it's hard to tell from the plots. There's so many to see how
Well,
significant.
that's where the chi-squared for the decays, and previously we have the chi-squared for the spectra, which is typically much better, but
Right.
we have the numbers in the paper, so I can tell you for each.
Oh, no, it's okay. I was curious. So you're saying that there is at least a marginal improvement in the trajectory to fit the
Yes.
masses,
Mhm.
because the other models just don't begin to fit the decays. So there you're really ahead of the game.
I didn't follow. What was the second comment?
Well, the additional comments I was going to make were to make two suggestions for additional things you might do where there's a real gap in standard theory or phenomenology, I should say. One is in the particle data book section on quarks, figure 15.4 lists all of the known resonances and, well, the ground state and the resonances, and compares it to the predictions of quark models. And the quark models predict many, many more resonances that are
Well,
not.
excuse me, I don't think that the quark model predict any of these excited states.
Oh, sure it does.
And
a standard quark model.
ground states,
Sure,
but
no. Quark models people have for years, I'm not talking about the masses, but whether they exist as states. But people have, just like in the hydrogen atom, that's the level. But anyhow,
do you say that the quark model produces rigid trajectories?
No. I'm changing the subject now. So you answered my question about the trajectories, and I completely agreed with you that your model is an advance compared to what people had in being able to predict so well the widths. But I wanted to change the subject to two things I think you maybe can do that would be very interesting. One is simply the number of states, these excited states of baryons and mesons, that have been discovered is far fewer than the number predicted by these quark models where you have like a hydrogen atom kind of a construction. And by a huge factor at the higher angular momenta. So if you had a rationale for why there are the right number of states, that would be a very interesting thing. So you could look at that. The pertinent thing in the particle data book section on the quark model is figure 15.4. So that was one comment. And then the other thing, I was just recently, for totally other purposes, looking at the data on E plus E minus goes to PP bar and lambda bar. It's an example, of course, that's dear to my heart, that the data absolutely confirms my prediction of years ago that I wrote up with Brodsky about the asymptotic behavior. But there's a very big puzzle about the behavior closer to threshold. And so your model, the data is very surprised, people are very surprised, they still can't fit it. Your model the string model seems to be a much more general function that you could use at much lower, much closer to the kinematic threshold. So you might look at that and see if you can explain it.
Yeah, that's definitely something that I should look at. I mean, let me mention something else related to the quark model, since you mentioned it, and that is the computation of magnetic moments and the computation of the mass difference between charge and neutral hadrons. And we are now with students who are working on these two questions. So the quark model did very well with the magnetic moments. But by the way, the lattice calculations are not so extremely well, but this is something that we try to do also in using this stringy picture and this decay to proton antiproton. Yeah, that's something that well, there is recently this 1855 resonance, probably you heard about it, and which, well, the question is whether there are some excitation to that which will decay to proton antiproton. But yeah, I'll be happy to talk to you about this. This trying to adopt the string model to this plus and minus results.
Thanks.